Okay, welcome to our second ITS workshop. So I guess Michele knows how it works. So he has been here for a long time and attendee and speaker multiple times. But I think that after COVID, kind of we forgot how things were like before. So it was really great great way to rebuild the community that we have been together. And so as today we have the focus today will be mostly on electronic software calculation methods, new advances, and also interesting developments. I have to first claim that I have no idea of how actually the calculations are being done. So it's pretty much the topic that I'm least aware of. But I think I have run this workshop long enough, so at least I can understand important methods. And so today we have pretty much speakers only on local and also one great speaker from Georgia, Joshua Richmond. And so we'll be talking about today embedding machine learning and also dynamics of many-electron states. And so as the first speaker, Michele Cabanello from Rutgers, New York, will talk about making and breaking electronic structures, opportunities from machine learning and orbital-free embedding. By the way, so this is pretty much like retreat among experts and also attendees. So we have ample amount of time. So the job for the speaker is to be able to deliver all those things that the speaker wanted, even with many questions and interruptions that we may have. So the total time will be so as you can. So I before the 10 minutes before the time ends, I will let you know. And other than that. So really exciting and also very informative workshop. And also another thing that we started trying from this time is to record all the presentations through Zoom. And then after the workshop is over, the recording will be uploaded sometime in the future. So in the end, we will actually have much larger audience than here because I mean last fall and spring I was on sabbatical and then was traveling in Korea and then I saw visitors from India and Japan and they say they saw my workshop workshop recording. So once it is recorded, you cannot recover that, but I think it's the video of the recording. But hopefully everyone will enjoy. So I hope that this workshop will be great. I mean, create great interaction and also help us understand to learn more about exciting developments. So with that, let's first then Michele, yeah, it's your floor. Thank you.
Thank you. This is great. I remember this room being full of people in pre-pandemic times. Yeah, it's really a privilege to be here, and I think you're right. This is our community, so it's our duty to build it, right? Keep it healthy. So it's great. Okay, so let me tell you about what I do. I don't need to go through all my slides. I'm very happy if I just go through some, as long as we have a good conversation. In fact, people in the back, if you'd like to come to the front, now is a good time. But actually, maybe we can convince you during the talk to come closer here. What I should tell you is that I strongly believe in reproducibility. And this talk is no exception. In fact, this talk is a code. And you can reproduce this code on your own, well, provided that you have Jupyter notebooks. And if you just take a minute to scan the QR code, that will take you to a GitLab repository where this talk resides. So please go ahead and yeah, snap a picture of that. Yeah. And if you cannot reproduce it, let me know. The people in the back. Did you snap a picture of this? Great. Okay, so let me acknowledge the people who did the work. Two of them are right here. And what you see here, Jessica and Shusheng. Jessica is here and there, and Shusheng is here and there as well. And then, of course, we have many other members that I really owe a lot for their work, daily work, against all odds, and collaborators that have been absolutely fantastic to keep us excited, to keep us kind of always up there. Oliviero, Mark, and Francesco. Of course, the funding agencies, without them, couldn't do anything. Okay, motivations. I think if you are an electronic structure theorist or someone who runs simulations, I think you're frustrated. I am frustrated because the real world is this. And unfortunately, when we run our simulations, we don't model this. We never model the real world. We model something that is much, much, we model model systems that really have nothing to do with the real world. Just as an example, here we have characteristic length scales, 500 nanometers, 100 nanometers, let's say. That's hundreds of thousands of atoms. If you put them one next to each other, looking at hundreds and a certain volume, hundreds of thousands of atoms. Nanoparticles, when we talk about nanoparticles, are they really nano? They're not nano. They cannot fit in your Gaussian calculations, right? They are very much meso. Right? So this is a major frustration that I would like to at least give it a try. See if we can kind of bridge what we have today with what we should do in reality. So we look at what's out there, what are the methods that we can use, and our goal is the electronic structure, but we can get there in a number of ways, or maybe using a combination of a number of ways. Here there's Concham DFT as the king of the electronic structure methods. However, not everybody agrees, and of course we also have wave function methods. And what you see here is the computational scaling of these methods. Concham DFT scales like NQ, wave function theory scales like at least n to the fourth, where n is some sort of measure of system size. What they don't tell you is that the prefactor that goes and multiplies that n is huge. And that really is the thing that stops you from modeling real systems. And there is something called orbital free density functional theory, which I'll talk to you today about. And this scales like essentially n. Yeah, of course, it's limited to what it can do, but it's certainly something that is interesting. We also have kind of fringe, I'm going to call them fringe method. Please don't get offended. Something like PCM, it can take care of environmental effects, but not just solvent, also conductive nanoparticles, and it can do quite complicated things, but not electronic structures. Same with MM, can do a number of things, just not electronic structures. There's something called machine learning that can do everything and nothing, right? Okay, how do we use this? Okay, so this is the typical paradigm. You run your DFT calculation, you want the solvent, you add PCM, which is a polarizable continuum model. If you would like to have some sort of specific interactions and maybe something that is not really polarizable, then maybe you can use some MM. Okay. This has been extremely useful, has been so for many, many decades. It's not suitable for mesoscale systems. And when I say mesoscale, I mean anything that you can think of and that is real. Okay. things that are not real, you can model. Right? Okay, so a better setup for the modern world, what would that be? That would be something like this, where you have some sort of connecting medium, which is something like quantum, something that has to be quantum, that is able to let all these methods talk to each other in an efficient way. You may have a Conchan DFT instance, or you may have a million Conchan DFT instances talking to each other. Same with PCM, same with machine learning, same with wave function theory, and so forth. You really want to achieve this. How to do that? A trivial way to do it is by simply writing the total energy of your system as the sum of these subsystem energies plus some sort of non-additive energy. And the connecting medium really is this non-additive energy, right? Is the nature of this non-additive energy. Okay? It has to be quantum, it has to be fast, it has to be accurate. This is what is required. N-orbital free DFT, and from now on I'm going to call it OFDFT. N-orbital free DFT work as connecting. Certainly could be interesting. Orbital free DFT, what is that? Well, orbital free is like DFT, but we just one orbital. Now you see, if you can reformulate quantum mechanics to just have a single orbital, mean field, single orbital, then all of a sudden you can see that maybe I can save some computational time, which is really important for the role that this connecting medium has. Okay, how is it? What's the theory behind it? It's, well, the variational function is just simply the density, which is given proportion, is essentially proportional to the square of this orbital. Single, no matter how many electrons you have. Imagine that you just occupy your first orbital 200 times, right, with 200 electrons. You learn in GenChem that you cannot do this, because that is a Pauli principle. But DFT is a weird theory, the theory of maps. Actually, it turns out you can map a bosonic system to a fermionic system. It's totally fine. Totally fine as long as you have the energy functional that makes it work. So we already know in DFT, and I'm assuming we kind of know DFT, or at least we are familiar with it. If not, just raise your hand and tell me, oh, I don't understand this in that. Take a step back. In DFT, we already have this guy, which is the exchange correlation energy functional. All that does is to map a set of non-interacting electrons to a set of interacting electrons. Here you see we also have a kinetic energy density function. That kinetic energy density functional, which we don't see in the written as a pure function of the density. We don't see it this way in DFT. Because now when we write it this way, we are assuming that we also have a map between a set of non-interacting bosonic electrons, which do not exist, but also non-interacting electrons do not exist, to a set of non-interacting fermionic, so bosonic electrons, fermionic. So as long as we know this function, we get this. And then we just brutally minimize the electronic energy to get the ground state density. Great. One, nowhere here we are diagonalizing. There is a single variational function. Two, complexity of this can be kept n log n as long as the complexity of each one of these functionals is kept to an n log n cost, where n again is the size of your system broadly defined. Okay, like I mentioned, we know that this TS exists by this functional theory, maps, and theoretical ideas, but we don't know what it is. We don't know the exact form of this function. Okay, as a function of the density. Well, then you are familiar with the Jacob's ladder of DFT, where you have exchange correlation functionals that can come with different complexities. You have the local density approximation, which I put up here, where essentially the potential associated with this functional evaluated in a point R is only determined by the density evaluated in that same point. This is good, it's a good approximation, but it has a lot of limitations for the exchange correlation. For the kinetic energy, this is not a good approximation either. It's called Thomas Fermi function. It's not a good approximation. It's a lot of problems. A semi-local functional is one where its potential in a point R is given by is determined by the value of the electron density in a small neighborhood around that point R. This is much better. Some people would say this is essentially where you should stop. But if you consider non-local functions where you actually they depend on a finite neighborhood of points through a convolution type integral like this, where you have a kernel function and then the density, and that gives you the value of the potential in point R, these are the most accurate functions. They are also more expensive. So there are a number of options for your functionals. We have done a lot of work in this area. You can decide to take all of these papers or just simply read a ChemRev. Now, this ChemRev is not yet available, but maybe tomorrow. Okay, so there are a number of non-local functions you can pick. Non-local functions with density independent kernel, meaning you pick a kernel that you can neglect the density dependence in this kernel. These are great functionals for uniform systems and metallic systems or uniform electron gas, of course. But molecules, not good enough for that. But you can take non-local functions with density dependent kernels, where the kernel now has a density dependence. And there are a number of options out there. We also did one, actually two. This one is, what is the other one? Maybe this one? No, yes, this one. This is the other one. Of course, it's much more accurate. And you can wonder how accurate is that? I mean, we are trying to describe the many-electron electronics, the electronic structure of many electrons with one orbital. How accurate is that? The other question you can ask is it really much faster than regular DFT? I mean, here you have a non-local functional. Is it really much faster than regular DFT? You can at least wonder, no? So I say, well, let's answer questions, right? We're here to answer questions. First question we can tackle is, how hard is it to run an orbital free DFT calculation and how fast is it? To run an orbital free DFT calculation is very simple. It's just a regular DFT calculation. You generate your model system, you set up an orbital free DFT simulation, you pick a kinetic energy functional, you pick also a exchange correlation functional, you pick, because we like to do condensed spaces, we do everything in plane waves, we also have to pick a pseudo potential, because when you use plane waves, you're stuck with pseudo potentials. And we need to define total energy function and minimize it. Easy. Okay, so I thought, since we have time, I thought you would do that today as well. So here's another QR code that you're welcome to snap a picture of that as well, because I will come around and check whether you guys are running the simulation. So please, this will take you to a Jupyter notebook in the Google Collaboratory. Especially you guys in the back, you were hoping not to do any work today, but unfortunately, you need coffee in the other room right there. Did you guys get the notebook? Yeah.
Is there a Wi-Fi in the room?
Yeah,
It's a Kuni.
yes.
Okay.
Or you can use everyone.
Wait, if you ask this question now, it means that you didn't take the QR code of the.
No, it's same
Which
like the
could-
party.
Ah,
Oh.
okay.
Uh-huh.
Okay, say. Okay. So I'm assuming you guys all have access to this Jupyter notebook. So we're gonna go through it together. The very first thing to do is to generate a model system. So we use ASE for this. You know, we like Python. We use ASE. We get simple aluminum cubic cell. This is FCC aluminum. It's not the primitive cell, but is the smallest cubic cell you can make for this particular phase of aluminum. Now, in the collaboratory, you don't have access to this GLUT NGL rendering, so you won't be able to see it, but you'll still will make that the same input file. You can still hit view ions. Maybe that will work. I'm not sure. It may not, actually, may not. Now, just checking. Was this successful? Did you guys run this cell? I'm just gonna go around and check, just to make sure. Nice. Great, that looks like it's working. What do you mean it's not working?
Yeah, if you have, for me, if you have do you happen to have the link?
If you do you have a cell phone?
Yes, but Rayon doesn't do that.
It doesn't do that.
No.
Okay, I do have a link. Do I have a link? It's probably a very weird link. This is the link. Where can I put it? I mean, it's a weird link.
Is the way to search from collect?
No. No. This is an interesting problem.
I can put it on the website.
Okay. What's your email address?
Abhishek, APHI.
This for a second.
HI,
HI,
SHEK,
SH,
UK,
okay,
654,
6.4.
r@gmail,
Right.
r@gmail.
Oh, sorry.
Yeah,
Go ahead, go ahead.
yes, @gmail.com.
Okay, send it. Bring this back. This back. Back. It's back. Okay. Okay, so I sent the link. Yeah, you get it? Okay, great. So you have it on the web page of the of this thing. Okay. Okay, so we have this. Next thing is to select an engine to run an orbital free DFT calculation. And today, you guys are going to use DFT-Pi, which is a orbital free DFT software specific, software entirely in Python that can run actually a number of different workflows, not just simple energy minimization, things like that. Can do all sorts of things, including time-dependent orbital free DFT for spectra and dynamics, but we don't talk about that today. So if you are interested, you can just go to dftpi.rutgers.edu and evangelize yourself on DFT-Pi. Okay, so let's do this. What we're going to do here is essentially to make a grid of points, 24 points in each direction, in each lattice direction. We're gonna define a local pseudopotential, which is what you need for orbital-free DFT calculation, and actually even for Kohn-Sham DFT calculations. We're gonna generate an initial gas density, which is just simply a uniform electron gas density, a flat density everywhere. We define a Hartree functional. You're free to define any functional you like, an exchange correlation functional. If you want anything beyond LDA, you're going to have to install libxc, I think. Anyway, Xuesheng has written a large part of this code, so you can, if something doesn't work, ask Xuesheng. So let's see, here it is. Now I have my pseudopotential. Then I have to pick a kinetic energy functional, and here we have a choice. What do? We stick with the semi-local functional, like Thomas Fermi plus von Weizsäcker, or we do a non-local. Let's go with local function. This non-local function is called 1 tether, which is great for metals, bulk metals, really great. Okay. Now, before I move on, I just want to make sure everybody's on this task. Are you guys at this stage also? I think if you had it on your computer, I think it's very easy. On your cell phone, maybe it's a little more clunky, but still doable.
So why do you go non-local if you're doing them both better?
Because you would never be able to reproduce the metal correctly with a local function, actually.
Or so are we doing where we have the explicit kernel, density dependent kernel?
Independent.
That's it.
Yes. Density dependent would make it about maybe 10 times more expensive. Still the same prefactor, so it's still the same general scaling law, but with a larger prefactor. Okay, so you see, we're putting together all of these functionals, adding them together. If you have another functional that you like to add, you can just do combine and add it. That's as easy as that. Python, being an object-oriented language, allows us to do this kind of stuff. Okay, let's do it. 474 milliseconds to get the electronic structure of aluminum. Okay. With a non-local. Okay. Not bad. The obvious question is, how does it compare with regular DFT? And now we are transitioning to a part of the calculations that you don't have. Okay. So I didn't make a Google Colaboratory version of what I'm about to show, but I can upon request. Okay, so let's run a quantum espresso calculation of the same system. Of course, we made a Python version of quantum espresso because remember the vision of having all of these methods sitting at the same level, being able to interact with each other. We have to have a common language to have them interact. The common language, we picked that common language to be Python. So we have a full-fledged Python version of Quantum Espresso, which is not a wrapper of Quantum Espresso. It's actually Quantum Espresso in Python. Okay. And you can ask Xuesheng for questions because he is the sole author of that. Okay, so that's called QEPy. We're gonna generate a QEPy driver. Here, I'm not telling you too much, but the bottom line is, of course, we need, unfortunately, an input file. Quantum Espresso is a bit, we need an input file to initiate it. The bottom line is that we're using the same grid as orbital free DFT, 24 by 24 by 24. This is equivalent to a cutoff of 80 Rydbergs for the density. And we have, of course, we need K-points because we have a condensed phase metal. We need K-points. And I don't know, for some reason, we get 666 irreducible K-points. I don't know why, but that's what we get. So first we need to diagonalize. And I think this is a great time for a coffee break. I will come back. Coffee. It's not going to take too long, but it's Kohn-Sham DFT, so you have to initialize the wave functions, you have to build your Hamiltonian, you have to diagonalize that with a very rough initial guess, which means it takes many micro iterations. So we just wait. That's going to be done by now. Should take about 50 seconds. Okay, 54 seconds. How many seconds did the orbital free DFT calculation take before? I forgot. I think it was 400 milliseconds. But this is only one diagonalization. How many do we need to do in Concham DFT? Many, because you have to reach self-consistency, so you have to run many cycles. Okay, well, let's do it. So we mix. We have to do density mixing, otherwise you will never converge. And wait, I gave it away. Then we have to diagonalize some more, because you see this SCF error, still not good enough. We have converged the orbital free to 10 to the minus 6. We'd like to converge the quantum espresso, the Concham DFT, also to 10 to the minus 6. Indeed. Okay, the second diagonalization is much faster because we have much improved initial guesses for the wave function. We mix again, and now we have about 10 to the minus 3, so we need to do another diagonalization. And then another mix. Okay. Just to remind ourselves, we're trying to answer some questions about orbital free. Is it much faster than Concham? Is it as accurate as Concham in some limiting cases, at least? Okay, so now we are 10 to the minus 6, so we're in good shape. We can move on. Now we have a density from Concham. Okay. What we notice is that Concham is much slower. For this small system, what do you think happens when you have a very large system? It will become progressively slower with a larger system. And orbital free DFT will be progressively more convenient or less expensive, less and less expensive. So let's look at the quality of the electron density. This is what we've been asking about. How good is orbital free DFT? And here, remember, we have a common language between these various codes. So now we can make them talk to each other. One of the things you can do is to compare the electron density between Concham DFT and orbital free DFT. Here, we just retrieve the electron density from Concham directly from quantum espresso. We put it on a NumPy array, essentially. Then we take the difference between the Concham and the orbital free density. And then, okay, we save it as a cube file. You don't have to, but you can. Why not? And then what you do, you take the absolute value of this density difference. You integrate the overall space to just determine how many electrons have been displaced. And now the density difference is positive and an equivalent amount of negative, sorry, positive and equivalent amount of negative density. So we just simply divide by 2 as we should. And then we compare against how many electrons we had originally, which is the integral of the density. Multiply by 100 to get a percent value. Let's do it. 0.4%. So this density is essentially identical. If I increase the K-point mesh in the quantum espresso part, this number actually gets smaller, which means that actually the quantum espresso density has not converged.
So is orbital free DFT also done in K space or in real space?
This is a great question. Can I not answer it? Do you mind? I'd like not to answer it because it would take us on a tangent.
Okay,
We can talk.
okay, sure.
Great question. Okay. You don't have to believe the little calculation that we just run. You can just read a couple of papers that we wrote on how accurate is orbital free DFT if you do it right, not with the Thomas-Redding function. And what you see is that actually you can reproduce surface energies of silicon, germanium, and 3,5 semiconductors. You can reproduce the geometry of a reconstructed surface of silicon 111. Crystal diamond silicon cup in the 111. Face it. How accurately do we represent these quantities? Not super accurately, but the trends are there. If you wonder whether the 111 facet of silicon takes less energy to cut than the 110, well, orbital free will tell you that and will be in agreement with Concham, independently of the pseudo potential that we use. right? And you can see the same type of behavior across. The trends are correct. So let's call it semi-quantitative response. We don't have 3 digits. We have maybe 2 digits. Pretty good. For 100 milliseconds versus not being able to do it. Right? Okay, then we can go big. You may wonder, Python, you will never be able to run a real scientific simulation with Python. Okay, what about 1 million atoms on a single CPU with Python? Is that okay? Is that? I think that already is quite convincing. Of course, we can always parallelize it trivially, and we do. Interface polarization of composite materials. I don't want to tell you too much about this. Suffice to say that we have the correct direction of the charge transfer between these surfaces. It's not trivial at all that orbital free will put the energy levels in the right place, but it works, at least for what we try. Nanoparticles, you can see we increase the size of the nanoparticle and we compute the energy per atom until we reach convergence to the energy of the bulk system. And we do that reproducing known models. So it's a physical method, delivers correct physics. So there is no reason to believe that orbital free shouldn't work as this connecting medium between subsystems of different kinds. May those be Kunshan DFT, may those be wave function theory, may those be other things like molecular mechanics or something else. Sure. So this will work for systematic equilibrium and out of equilibrium. I didn't show you, but we did also. We developed a time-dependent orbital free PDF, orbital free DFT, which delivers in every respect a similar picture to the ground state results.
Yes. Yeah, something more basic. So see, orbital free DFT, so you represent density in terms of grids, right?
On the grid?
Yeah, okay.
Yes.
How do you?
Conshan does the same thing.
Yeah, sure. So what's the, given problems, as the system becomes larger, then you actually will need a lot of, a number of grid will.
So if you have a 100 nanometer system,
Yes.
you need to be able to represent a grid
That
has that dimension.
Yeah.
But the beauty of modern computing architectures is that you can parallelize this in a smart way, not in a trivial way, in a smart way, where you never really, at any point, you never have a gathered array where the whole grid is gathered on one physical unit, or a hardware unit.
Yeah.
You always, you distribute the grids and you never gather it. So as long as you have a big enough computer, you should be able to do it. In fact, for 1 million atoms, I think all you need is about 1 terabyte of memory, which is now standard, even on single. If you can distribute that, if I have 100 of these nodes, then I can do 100 million atoms.
And what's the typical size of each grid for the calculation to be actually?
So right here, actually, this loaded question, it depends on the pseudo potential.
Sure. Yeah.
And I would say you will never use a pseudo potential that requires a very fine grid, because that would be contrary to the idea of doing large systems. So you have to work on many levels. But you saw here 24 by 24 by 24. So you're looking for a small system is about 1,000, right? 1,000, 5,000. If you go to a larger system, and
so it depends critically on the nature of pseudo potential.
Yeah, the pseudo potential is very important.
But isn't the pseudo potential also kind of based on some kind of fitting at small scale?
Yes. Okay, so raise your hand if it is clear to you that the grid size is dependent on the pseudo potential used. Raise your hand if it is clear. Okay. Great. Only 2 people, which means it gives me the opportunity to explain this. Pseudo potentials, maybe. Pseudo potentials is another way to represent Coulomb interaction of electrons to the nuclei. And you would think
Yeah, we'll see about.
Here it is, here it is. You would think, actually, I did it wrong, it should keep going this way. You would think the Coulomb interaction goes like this, right? Which means it goes to minus infinity at the point of the nucleus. But how many, and you have a grid, right? You have a grid where you have a point here, point here, point here, point here, point here. Doesn't even matter having a point at 0, doesn't even matter. You're not gonna be able to represent the singularity. You're not. So what you do this. Something like this. And of course, this is not Coulomb anymore, right? This is a pseudo-potential. It's not Coulomb anymore. So you guys cannot see anything. I'm the only one who can see stuff. Thank you. Coulomb. Pseudo-potential. That smooths that singularity, makes it smooth. And then still goes like 1/r here. The singularity is smoothed. Obviously, the interaction of the electrons close to the nuclei will be different from the real Coulomb interaction. But you account for that in the shape of the electronic structure. The shape will be slightly different, but you can account for it. Okay. So if this pseudo-potential is very smooth, you need many less points. If it is very hard, for example, if you're interested in semi-core states, then you need many more grid points. Many more grid points. So, in my lab, generally, you're interested in the valence electrons, not so much the semi-core, and so you get away with smooth pseudo-potential.
Yeah, okay.
Okay, I mean, this is all details that are really important. Okay. Hey, let's use this. We have orbital free DFT. That works. Let's use it. What do we do? Well, the very first thing we want to do is to connect Kohn-Sham DFT instances. Right? We want to have maybe here I put 3 Kohn-Sham DFT subsystems interacting with each other. And how would we do that? In the same way that we discussed before. We write the energy as a sum of subsystem energies. And this Ni are the electron densities of each subsystem. And then we have a non-additive energy, which we're going to evaluate using orbital free DFT. So this connecting medium is, what we're going to do is to use orbital free DFT for this. What does that mean? What is this non-additive energy? Well, is a non-additive kinetic energy, a non-additive Arterian exchange correlation, and of course you have Coulomb interactions. Classical Coulomb interactions. Are we missing any physics in here? No. The exchange correlation non-additive contains all the physics that you would like. Van der Waals interactions. Anything that you like. Of course, you have to have a function that represents that physics correctly in order to see it in the end. That's a different story. In principle, it's all there. What is this non-additive kinetic energy? Is what chemists call Pauli repulsion. It's always positive. But it's not an ad hoc quantity, it's an actual. This is all theoretically exact. Okay? Assuming that we have access to the exact functions. Of course, we're going to use approximate functions to run the simulation. So, if you have, say, 10 subsystems, you can do it on your laptop. But I didn't make a Jupyter notebook for that because you would need a parallel version of what we did, and Jupyter notebooks and parallel, I am told, they don't really go well with each other. So, well, we can connect many Kohn-Sham DFT subsystems, say hundreds of subsystems. It's doable on your cluster. Whatever cluster you have access to, you can do. So we did a number of things. We did things like, well, I'm going to go a little faster if you guys know. Oh, no, yeah, I should tell you about this. We implemented this in a couple of ways. One way is Fortran, because when we started this business was about 2012, and Python wasn't really something that people used that much in science. PySCF came in 2015, if you remember, if you were around. So then inevitably we thought, we need a common language for all these things. So we have to implement density embedding where you have orbital free and then these subsystems in Python. And EDFP5 is what is the software that makes that happen. And that's a software that takes care of this really fancy parallelization that never gathers data on a single CPU. And that's also due to Shushank. So it sounds like Shushank should have talked about this. And you may wonder, what are the timings? Does this really work? I can give you a hint why this will work. When you do orbital free, all you care about is the electron density. The electron density grows linearly with system size, right? Because you double your system, you double the grid points, double the memory, double the amount of data. And it's a local quantity. Okay? Which means when you need to broadcast some electron density to build functions, to build these non-additive energies, you broadcast an electron density that is a very easy thing to broadcast. So you can go really big and not feel slowdowns due to these communications between units of your cluster, right, of your high-performance computing cluster. And this is identified by this plot. Look, we have EQE and EDFT5, both subsystem DFT. We use increasing number of CO2 molecules, it is condensed phase CO2, an increasing number of processors, or NPI tasks, the ones we who code. What you see is that regular quantum espresso and any Concham DFT software will show an increase in computational time because the broadcasting of this data goes beyond the electron density and includes also wave functions, which grow in system size. And subsystem DFT is flat. Great. Actually, you will notice that the Python version is below the Fortran version. We can talk about it later. But a victory for the Python implementation, I think.
What's the main reason?
For what? The Python being lower?
Yeah.
Because the parallelization is much more mature. The Fortran version had a gather-scatter type parallelization. Okay. I think I've convinced you this is the way to go. But is it accurate? It's much more accurate than you would think. This is the S66 set. Among the chemists among you will know this. You have a method that can connect two things, and these two things are weakly interacting. You want to test your method on these established test sets. S66 is a very respectable test set for this type of benchmarking. And what you notice here, I put, of course, I'm biased. I want to show you how good we do, and I want to pick a fight with the wave function guys, because if you look at our method, we have this LMGP, SMP, these are just non-additive kinetic energy functions, but it's just a detail of the calculation. Both of these histogram bars are subsystem DFT. And the accuracy in comparison with CCSD parenthesis T complete basis set extrapolation. You see that we do, with this function here, we get 0.8 kcal per mole, root mean square deviation. And for this function here, we get 1 kcal. How good is that? Well, if you run CCSD complete basis set limit, you get 0.7. If you have spin component scaled MP2, which is the golden standard for like crystal structures, 0.9. Okay, so we are doing really well.
So, in your subsystem DFT, do you have some components that is not in the standard DFT? Because I was thinking you want to compare to standard DFT. If this is a way to make DFT faster, the accuracy should be approaching DFT.
Yeah, standard DFT is, I mean, if you do 10, you're about here. And you can wonder whether that's error cancellation. But you can also wonder whether CCSD has error cancellation against oneself. But this is a fair comparison. DFT will give you similar results.
Okay, so because you don't have DFT here, so
Yeah.
you're saying DFT is like
0.5,
closer or
0.5,
saying-
yes.
Yeah, okay, yeah.
BD10 will give you 0.5.
So your subsystem DFT should be
Around.
similar of DFT, right?
Yes.
Okay.
Yes.
So what's the size of your subsystem?
This test set has a set of molecular dimers.
Okay.
So one molecule is a subsystem, the other molecule is the other subsystem. So two subsystems.
Okay.
This is just for measure
I see.
to see how accurate.
So in the limit where the subsystem becomes the entire world, it becomes simple DFT.
Yes.
But as you divide it more, then the scale of calculation improves, but then there is the error for the non-additive functional will increase as the subsystem size becomes smaller, right? So I would.
Let me tell you this.
Yeah, the real, I mean, theoretical challenge here is
Yes.
to understand systematically what's the error.
Yes,
caused by
exactly,
the non-
exactly. So you would never make a subsystem smaller than a molecule, than a connected molecule.
Okay.
You would never do that.
Yeah.
Because these non-additive kinetic energy functions are not good enough to describe, to break something where you have a covalent bond, as you would expect.
Yeah.
Because the wave functions are really interfering to get you the bond. And there are no wave functions in our DFT. So
Yeah.
okay, now you said something else, which is very logical, and that is as you continue breaking, you increase the error. I'm gonna debate that.
Okay.
Because what is the error? The error is your ability to exploit error cancellation. If your ability to exploit error cancellation is limited, you will make big error. So in the case of CCSD, for example, I like that method because that method does not really do such a good job with error cancellation. You can get really weird results because you're not hedging error cancellation correctly. When we split using subsystem DFT, we've showed this many times. Actually, maybe it's the next slide. This slide. We show that actually we can hedge error cancellation consistently to our advantage. One of the things that we know DFT is unfortunately plagued by is self-interaction error. If you have two water molecules, the hydrogen bond between these two water molecules will be, let's say, will be described in a way that is not accurate by DFT, by most DFT approximations. Here we hedge error cancellation. We cut self-interaction error completely, and we can talk about it, why that is. We can talk about that. If you look at our structure of liquid water, we run a molecular dynamic simulation, 256 water molecules in the box, push it for 50 picoseconds, and then we get some GOR. And you see that our is the red, the experiment is the dashed, we're on top. Regular DFT, not quite on top. This is a known failure of semi-local. So then why is our subsystem DFT working? Because we have a good handle on error cancellation. The number of electrons in each subsystem is integer at all times. And more often than not, in DFT, you break that integer number of electrons, and that pushes self-interaction. And this is a real thing that happens. In fact, there are some papers that came out from the Purdue group, together with the Paisani group, where they show that actually this is a single problem with water, with the DFT description of water, is the fact that the number of electrons in the water monomers become fractional, non-integer. When that happens, you can show by using NB-pol that gives you very accurate energies for any sort of water clusters or bulk water. You can show that actually your two-body energies for water become worse. The number of electrons in the DFT calculation for each monomer goes away from the integer. So it's a real effect. In fact, what you see here, also for fluid CO2, the vertical lines are the experiment. Subsystem DFT always reproduces the experiment. But PBE does not. You can say, who would run a PBE calculation today? But we need to
So,
know.
so for extended system with significant charge transfer between different things, how do you use subsystem
This is such a great idea. And it's such a great question. And I'm gonna ask a question back. How do you use DFT when you have significant charge transfer? It's problematic. People make careers on this.
Sure.
So it's not a subsystem DFT problem.
I know.
It's a DFT.
Yeah, yeah.
Actually, subsystem DFT gives you the opportunity
Yeah.
to localize charges on your subsystems and develop a diabatic version of DFT
So
in a very natural way. The DFT would require you to do maybe things like constrain DFT.
So it's not possible to assume fractional charge for subsystem?
It is possible.
Yeah.
Absolutely.
Yeah.
It is possible.
Yeah.
And that's an ongoing area of research. Because imagine you have an open system.
That also might be important for the water line, but because people are arguing about the nature of this hydrogen bond, whether it's charge transfer or just a pure Coulomb. So if you don't have charge transfer in your method, then of course it won't be due to charge transfer at all.
I agree with you completely. Like,
Okay, so
charge transfer is part of life, right? So it should be there somehow.
Yeah.
How to put it there? I don't think that has been solved. But even in the end. Anyway, this is
so
interesting.
when you said the EFT has it there, it just may not be accurate, but it's there. Right? When I should want to
But
make
it's
it
a
clear.
system DFT also is there. It's just much less.
So when you do subsystem, you are restricting it, not to.
Integer number, but the electron densities can be localized. So electron density in one subsystem can penetrate the region of the other subsystem. So if you run a population analysis, things may get non-integer.
That depends on what you mean by population.
Yes, we can talk. I agree.
So with respect to that last question, how are you defining or what basis are you working for your subsystem?
Plain wave basis.
And so is it do you have to work on the full basis of the
You can.
entire system?
You can, but you shouldn't, because you are banking on the assumption that the electronic structure of the subsystems is localized. If it wasn't localized, then this wouldn't work at all. And you would have to do something else.
But there's no formal issue about localizing the basis or having a different basis for each subsystem.
Of course, you can do it in principle. I mean, it's all about the initial guess, right? What do you pick as an initial guess and what kind of freedom you give to your business? The design choice of the method, if you wish.
It sounds as though if you have, let's say, an acid, individual water can transfer with the,
What happens if during a dynamics you have a reaction and you have covalent bond forming between formerly two separate subsystems? We have developed something called adaptive subsystem, which I don't talk about today, but we have it, where essentially we have learned a way to make and break subsystems along the way, while still maintaining an acceptable level of energy conservation in the dynamics. But this is a detail. Good question. I don't know how long I have, but
So you have a 20 minutes, so if you want to talk about machine learning part.
yeah, that's what I'm. I think I would.
So I think before doing that, maybe one about, so subsystem DFT is a particular way of doing embedding, right?
Yes.
Or maybe more general way, if you, from your point of view.
The connecting medium can be anything you want. It
Sure.
can be something
Yeah.
that is based on the reduced density matrix, and then you will get something else.
Yeah,
Right?
yeah. And then the beauty of that is, it's kind of like linear scaling in terms of that, because
Right, because orbital free is linear scale.
Yes. So when you, but the non-additive functional, it's the kind of the accurate part of the, I mean, the subsystem DFT. So has there any progress in, I guess maybe why don't you use machine learning to
get the non-analytic function. It's a great idea, and I would hope that the audience would work on this so that it can be improved. Yeah, at some point you have to move on, right? I mean, you do something for 10 years and then it's like, okay, I'd like to do it. And here we worked on these kinetic energy functions for just about 10 years. And what was it? 0.8 kcal per mole? That's our number. Yeah. But this is reality. Millions of subsystems. Okay. Maybe we can do it having a very powerful high-performance computing machine. Maybe there are 2 or 3 computers in the world that could approach a setup like this. Not interesting to me. I think exascale is really something that it's overrated. Yeah. Who will take advantage of exascale? Maybe one person in this room, maybe less, a fractional number of persons in this room. But it's really not something that is useful. So I don't like it. Who's taking it? Someone talked? Siri is interested. Siri is interested. Of course, Jeff Bezos is listening. Okay. Millions of systems, that's where we want to go. It's clear that your cluster will not be able to do this. My cluster won't be able to do this, and so yours. Okay, so machine learning comes to the rescue. We need a fast and accurate electronic structure method. Solver. Can we avoid SCF? Remember how long it took to diagonalize? Can we avoid it? Can we avoid any other post-SCF solver? We want access to anything that a regular electronic structure solver could deliver without touching the electronic structure solver. So how do we do it? The goal is to predict or learn the electronic structure. Okay, how can we do that? We exploit formal maps from density functional theory. Formal maps are as follows. The external potential yields the electron density. Okay? We have seen, we first had to build the nuclear position, assign a pseudopotential, and then we could build the electron density. So there's the external potential, which is the potential of the nuclei, delivers an electron density. Well, that map is unique, and we can learn, can be learned. And there are a number of papers that show from the groups of Mark Tagerman, Kieron Burke, and Klaus Miller, they show that this can be done. However, there is another map that really would be needed, and that is the density to energy. And if you just have, that map exists, but we don't know. We wouldn't be able to compute an energy function because we don't know, we know it exists, but we don't know what it is. So using the density alone is problematic, as the electron density to energy map is unknown and needs to be machine learned. Instead, we can use the one-body reduced density matrix. This is a much more powerful quantity. In practice, in theory, is the same as the electron density. In practice, it's much more powerful. There is still a map to be learned, the external potential to 1 RDM map. But the map between the 1 RDM and the energy functional is usually direct. It is, for mean field methods, the energy is solely a function of the 1 RDM. For non-mean field methods, this map still needs to be machine learned, but we are okay with that. The nice thing about the 1 RDM is that you have access to natural orbitals. You can localize those if you wish and get something that is useful. And you can compute any 1 electron observable trivially. Much more powerful. And this is something that literally came out last week. We did this with Mark Harren. Okay. Learning the one body reduced density matrix. How do we do it? First, we start from, we pick a molecular system. We need to develop a training set to learn the external potential to one body reduced density matrix map. Meaning we have to move the molecular system a little bit, explore configuration space enough that that gives us a representation of the configuration space accessible by that molecule at a certain temperature. Then we just simply do a regression to learn the map between the potential, the external potential in GTO basis, and by the way, these are actual matrix elements of that, with the one body reduced density matrix in the same basis. And by the way, these are the matrices of actually the one body reduced density matrix for, I believe this is water. We pick GTO basis because it's just a lot simpler. We use PySCF for this, that is super easy to use and frankly easy to develop. Once we have these high quality 1RDMs, because we have learned this map using a particular type of regression, then we can use it by just simply using trivial quantum mechanics to get expectation values of one-electron operators, DFT energies and forces, concha Hamilton and band gaps, orbitals, whatever. No SCF, no diagonalization. But we can also learn maps directly to, again, DFT energies and forces if you would like. You know, to get these DFT energies and forces, you still have to build certain matrices. So you can avoid that altogether if you wish, don't have to. And if you have wave function theory, meaning post-Hartree-Fock methods, then you have no choice, but you have to learn that map to energies and forces for those methods, unless you learn the 2RDM, and you can talk to Jessica about that, but we're not going to talk about that today. Okay, so this is so far, I think, quite trivial, no? External potential is a matrix, 1RDM is not a matrix, same size. I just run a regression, it seems easy. Okay, what does it take to reach chemical accuracy for this method? And are we okay with chemical accuracy? The answer is no, we're not okay with chemical accuracy. We want SCF threshold accuracy, which is very different from chemical accuracy. Remember, we want something that is exactly the same as, say, a Gaussian calculation. Chemical accuracy is 1 kcal per mole, and this is for the benzene molecule. With just about 20 or 30 structures, you can represent the 1RDM that yields energies that are within chemical accuracy. How many structures do you need to reach SCF threshold accuracy? You need about 10,000 structures. Okay, maybe you could get away with just 1,000 or 2,000. So really building this training set is really important. Is where the method is really. Because the theoretical apparatus of this is quite simple. And
So what's the difference between the two curves?
yeah, good question. Here we have two curves. For all purposes, let's just say that we use the orange curve. It doesn't matter. It's just different regressions. Why are 10,000 structures needed to learn the 1RDM to SCF threshold accuracy? This picture really shows it to you. These are normal modes of benzene. And the orange, normal modes. So you have, what is it? We take 29. And this is the displacement from the equilibrium geometry along a dynamic. So you run a dynamics, pick a temperature, you run a dynamics. And you're going to get a certain histogram of probability of having a normal mode displaced by this much or by this much, by that much, right? So you get these probabilities. You need to be able to represent those distributions with your training set. Not only that, you need to be able to represent also the coupling between the normal modes. Normal modes roughly grow as the number of atoms. The coupling roughly grow as the, what is it? You're running into trouble very quickly. Big trouble. All we could do, and maybe there are better ways to do it, we could get away with cubic scaling to represent configuration space of any molecule that we have seen you need to consider a number of configurations that scales with the cubic power of the number of atoms. This is true also for DFT, because when you run a dynamics with DFT, how long should the dynamics run for? I can tell you should run for long enough that you get those distributions and that you represent the couplings correctly, and that grows, in our experience, with the cubic of the number of atoms. Very interesting. Of course, we coded this, Shoshank, again, and you can take a look at this code. It's called QMLearn. Yeah, I'm just gonna move forward because I think we're running out of time, unfortunately. So let me just show you the case of 1-propanol. 1-propanol is challenging because you have rotational freedom of one CH3 group, rotational freedom of an OH group. That's a nightmare for configuration space. So we need about 40,000 structures for propanol. Okay, but then we have a model, a machine learning model that has a prefactor for evaluation that is abysmally small. So it's 5 orders of magnitude faster than the electronic structure method that it represents. And this is a dynamics, 2 picosecond dynamics. We use LDA, machine learned LDA, and LDA computed with a machine learned gamma. Okay? So this learns 2 maps, this learns only 1 map. They're essentially on top. They've been shifted so that you could see that they're indeed the same. That's quite good. 2 picoseconds is no small potatoes, right? 2 picoseconds. We conserve energy during a dynamics. We do this with an electronic structure method that is by all means the same as LDA, just 5 orders of magnitude faster and completely encoded in our machine learning model.
Is that for one molecule?
Yes.
Do you have to relearn if you have 2 of the same molecules? Like if you put 2 one molecule together, let's say, can you use what you learn from one molecule, or you have to relearn?
It's a great question. So this is what we're working on, actually. There are a lot of complications.
So when you say you are working on, it means that you have to be trained. If you use.
For every molecule, you have to train a model. Yes, yes. However, the model can also be transferable from one molecule to the other, as long as you are not picky about accuracy.
I see. And also it will take
So
some time.
imagine you have a model for, I don't know, CN. You can take that model and model N2. And you're probably going to get decent electron structure. You might get a slight dipole in N2 because you trained it on CN. So as long as you're not too picky, right? It's transferable within certain limits.
Are the bonds special in this transfer?
Then again,
Are hydrogen bonds special in this transfer? In a propanol, you form a hydrogen bond.
right?
And
Yes.
I mean, if you took propane, you have
Propane would be
percentage
easier.
rotation.
Yeah, it would be easier. Propanol is much harder. I agree. We picked propanol for this reason. We wanted to show you can still do it even if this OH moves and then gets stuck and then moves it. And it's quite a freedom in this OH motion. Anyway, this is the dynamics result. This is the IR spectrum of 1-propanol. We used the B3LEAP-ML. This experiment, well, means we had everything correct, except the intensities are not perfect. We blame that on B3LEAP. And if you wonder whether you can extrapolate outside of the training set, let me show you the band gap predicted by machine learning and the band gap compared with the real band gap, so LDA versus LDA. I love the band gap. And we take the OH bond and we stretch it, just to see. And the green histogram is the training set structures. They all fall within this region. And you can see that the band gap is reproduced also outside of that region. And for both for bethanol and propanol and Ah, great. That's extrapolative power, which is good. So it's not just about interpolating in that configuration space. You can also extrapolate for band gaps. For molecular dynamics, that's a totally different story. So let me take you back to this idea. Can we do this? I think the answer is yes. Then the answer is totally yes. We can do this. We can approach a system like this, where each one of these subsystems is a machine learning subsystem. An orbital 3D-FT can still be the connecting medium because we have an electronic structure for each subsystem. We don't just have an energy bar or a charge. Yeah, B1 at the end. Good. So the next 100 slides, we're just going to go through very quickly. And I'm going to thank you. Look forward to more discussion.
Yeah, thank you. So we have time for one question. Okay.
So I have two questions regarding the machine learning part. So one is you show the convergence of the energy, and I'm wondering because you learned density matrix first, and if you use density matrix as a convergence threshold, will that be the similar trend
Yes.
in the SAF convergence?
Yes. Similar trends.
Okay.
Although there is a
So-
nonlinear relation between energy and one at the
Okay,
end.
so you
the
know that
convergence
it's
trend.
like a linear kind of like more or less like a corresponding.
Correspond. Yeah, I think that's
It's
correct.
not like
Correct. Yes.
okay, got it. And second is I'm wondering, what's your thought on comparing this to the work that the Schnapp people do, where they learn thought matrix or Hamiltonian
Yeah.
of the
Okay.
molecular systems?
Yeah. We look at that.
Yeah,
It doesn't work.
I'm wondering.
So this works.
Yeah, I'm wondering what
That
makes
doesn't work.
what's better than that, right?
Ah,
Yeah.
why is this better?
Yes.
That's a good question. I think it's deeper. The answer to that is deeper than we think.
Okay.
It's much deeper than we think. But yes, you're right. That method doesn't work. This method works. Despite the fact that they use 8,000 geometries, so it's very similar.
Yeah, that's why I'm wondering.
Yeah, then in fact, so we started this project and I looked at that paper and said, oh, it's never gonna work. Then I asked, I talked around, it's like, no, it's not gonna work. And I said, but actually, I think it should work. So we did it and in the end it did work. But then we realized later some hints of why. What we said. Bottom line is that there is something special about the density or the one at the end.
So in the full SF limit, your matrix will become infinite. Right? And so the base set remains fixed. I mean, when you
Yes,
start
yes. So we use GPO basis, right?
Okay, I see.
Yes.
Okay, yeah.
So there is a limitation, right? It's not, I mean, every method has a limitation. This method requires GPOs. So you need to have a code that puts GPOs on the atoms. You can say, but that's slow. Okay, well, all right.
But how about the okay, I see. And
And you need basic elements.
yeah,
within this.
machine learning parts. What method of machine learning have you tried?
Okay. We tried a few.
Okay.
What you really want is a deterministic method. You don't want deep neural network. And I tell you why. Very simple. In deep neural network, you give one input one day, and you get an answer. You give the same input a little bit later, you get a slightly different answer. That's very problematic for say electron structures, because this electron structure will translate to an energy and a force, and if the force is noisy, things will get.
Yeah. So which deterministic method did you use?
Kernel ridge regression,
Okay.
which is similar to what Mark Tapperman and the previous
I see.
papers did.
Yeah, yeah.
And that really works. It really works. We have to tweak that a little bit for the one at the end, but essentially kernel ridge regression,
I see. Yeah.
which is deterministic, right? So you give the same thing, you get the same answer. Twice the same thing, twice the same answer.
Other question? Yeah, thanks for great help and also for keeping time. Yeah. So we have 10 minutes bathroom and coffee break, and then we will resume at 10:30, 11:30. Yeah. Tim, maybe you can set up your presentation. Okay, so our second speaker is Tim Wu from Brookhaven National Lab. And Tim is also, has been at the Graduate Center many times, and also he was also co-organizer of the many conferences that we had here at the Graduate Center. So it was called NITEC. and so Tim, so when did you start at Brookhaven? It was
2008.
2008. I see. Yeah. So he is now a senior chemist and or chemist at
Not senior, I mean, I'm senior, but it's not a senior chemist, it's a special title.
I know. Yeah. So chemist at Center for Functional Nanomaterials at Brookhaven National Lab, and he is going to talk about the DFT and machine learning, as you can see here. So the mechanics at the kind of the good stage for this talk, and then so we learn more about DFT and also machine learning. So thank you.
Yeah. Thank you, sir. Great to be back here. So like as Sophie said, I also actually came here many times for workshops and also the NITEC 3 conference.
Yeah.
The Neuro and Computational Chemistry conference.
Yeah.
And it's always I mean really appreciate Suki's effort to like bring theory and theoretical and computational chemistry here together, and then was able to discuss and exchange ideas. So I'm going to talk about some ongoing work, actually very current. So it's a lot of these things here is not published yet. Actually, we're still working on it. So the slide was really also kind of like in development. So maybe some, if you see some errors, then let me know, or something not clear, then let me know. Good thing is there's no quiz, so okay, so you don't have to worry about that. But feel free to interrupt me. Okay, so there should be give us plenty of time to for discussion. So and I only have 36 slides, so you have to help me out. All right. So I'm working with the experimental colleague, the CFM, to kind of understand, trying to find new ways to understand the surface chemistry mechanisms. Like so okay, so the temp corrections on surface is critical to I mean many things, of course. I mean like just for energy, I think we are DOE labs, so for energy labs, so I'm talking about is the process of chemicals like petroleum industry, or even like hydrogen evolution, or I mean new like renewable energy like sources like or fuel cell. Those are all surface chemistry categories. So we have a big interest in that, but they're all also very complex surface chemistry. Many things can go on there. I mean, even how the surface looks like, it's sometimes not a very it's very hard to probe, because wait, it is all true. I should have stopped at I don't know how I did not set up for the auto progression. Anyway, so the ongoing effort to build new tools to understand surface chemistry and especially the kinetics of it. And this is the one my colleague Annabelle Bosco Boyner just started to build last couple of years. So this is the designed to study the transient kinetics of what's happening in the surface. The idea is that you have this okay. I don't have, so I'm not showing the picture of the full instrument, because I mean we're theorists, so we don't really care about how the instruments are actually built. Oh, there is actually that's here, experimental, like formal experimental. So okay, Anyway, so so you have an IR chamber. So you have clean surface in this chamber. This is the sample, sample holder, and then this IR chamber usually is like a vacuum, ultra high vacuum, so nothing in there. But then you have this a kind of tube, caterpillar tube, which is connected to a valve. So you can just kind of inject some gas into this chamber. Especially if you make the tube like close to the surface, then this molecule that go to the surface directly, and then you can locally maintain some pressure there. And then once you have a molecule on the surface, then you can also add a probe, like in this case we use IR, so the reflection IR. So it's a surface, I mean, very small area. You have to the signal you have collect is only from the surface part, right? And so if you build a way for them, I mean, what they have done is find a way to synchronize these two, so the injection of the molecules and the IR. So if you can synchronize this, and then you have this transient kinetics, like kind of like pump and probe in other experiment. But here the pump comes from the gas pulse. So that's the once you have that, of course, you put the pump on, and then you observe for some time, and then you can just shut the valve, and then let the vacuum work and take the molecules out. Then you go back to your original state, so ideal. So this okay. This is the idea of the experiment, right? Now, for the challenge for them, one of the challenges is that it's again surface area. I mean, it's very small. Like amount of actually molecule is there, and if you want to get enough signals like on this sample, you need to have to expose it for a long time. So the IR exposed for a long time. But then if you have to run IR for a long time, then you lose the temporal resolution, right? So you don't detect what's happening in that your IR window. So the option what anyone has done is actually you take short IR spectrum, but then you have this thing like running cycles. So you basically have if you imagine you have a reversible process, like the molecules will first be absorbed, and then will be dissolved and then become vacuum again, and then you can run this experiment many times, and then now you take the spectrum at certain time of this process, this cycle, and you only expose it for maybe now 60 milliseconds. Right? For 60 milliseconds, of course, you don't get much signal. It's very hard to analyze the data. However, if you do this repeatedly in the same pattern, always at the same time point, like you have this time window, you always take a picture, means a structure at the same point of this process. Then you can add up the signals, like and take the maybe 400 of it. Like here, this is the idea of this. What you see, this black dot there, identify this point where you can take the picture. I mean, again and again, and then you add up all the signals. And if you do that, you get a pretty good signal to noise ratio. So you have a actually usable selection. Right? So this here is the idea. This is black the one single snapshot of the single spectrum, and this has been enlarged by 10 to the 3 1,000 times. Let's see how noise it reduces. But if I add up 400 of them, you get a nice peak. So that's the experiment, the background of what we are trying to do, and it's a really nice setup. And they're trying to do have ambitious to study many different reactions. But I mean, caveat, of course, it has to be reversible, right? So not okay. So that's the
So that's the typical size of the surface.
Surface size. Micrometers, I think. Yeah, I'm not very sure, but I think that will, it's very small.
And then the IR is taken on the surface. It's not near field, of course. It's just standard far field IR spectrum on the surface.
It's the reflection IR. The idea is like it's polarized.
Okay.
So it's a module. It's a polarized IR. So you only take the signal where you. I know this direction. So you can. That's how you get the.
I see.
They can like a.
Yeah.
Study the CO like a stretching instead of other things.
So then, each spectrum is pretty noisy. What's the source of that noise? Because you have to, but if it's average over 400 cycles, then you get pretty good spectrum. But normally in any bulk IR spectrum, you don't have to do that, right? Why do you have to?
Normally, I think IR you expose for seconds
Yeah.
or even longer time.
Yeah.
Not just like a millisecond. It's when you have very short like a exposure.
I see.
I don't know all the details of where the noise comes from. The instrument itself has produce enough noise to make a signal very.
So mainly the noise comes from the kinetics.
Could be, but part of it maybe
Yeah.
because during that millisecond time, 60 minutes, there's something happening also. But that part you won't be removed by averaging. If you just accumulate all the data, that part will just enforce itself, right? If it's the same kinetics. But when you take the average, then what's being like removed is really the random noise. So that's why you can get a better signal to noise ratio. So once you do that, you get spectrum something like this. It is really you have a time axis. You have this like spectrum with the frequency axis, and you have this absorbance like that. So it's easier to see it in the 2D. Of course, you have this color map, and it will show how this CO absorption happens, and also how it moves. CO actually move on the surface, like the interconversion of two different sides, and then finally it's dissolved because of the I guess I should maybe I forgot to mention the CO on off, CO on only for 2 seconds, and then you have this desorption burst because it's much slower. So you have to keep the valve off for like maybe 8 seconds or longer to make sure it actually dissolves so that it goes back to the original state. So you can do this at different temperature, and you can see this data. This is just the very this picture already showed that some of the kinetics you kind of expect. So it's a desorption process, which goes faster when you raise the temperature, for example, right? And so, but some of the things you don't really get if you don't have the transient kinetic capability. Like absorption is very fast. Okay, but people usually don't know how fast it is. But here I can tell you, like it happens in less than 0.4 seconds. So that's only available because of this new capability. And then on the end, also this like two sides. We know there are different configurations on the CO and the palladium, and how the interchange. That's also the kinetics of that process is interesting, but usually not available if you have this traditional surface techniques. That's usually measured at steady state. So basically now you have a very rich amount of data available here. A lot of interesting things happen, but then there's also a lot of challenges to understand this data. So it's particularly for the quantitative analysis, if you want to get something, what is the barrier height, or what's the rate of this thing. And we start with the two configurations. These are the what are the configuration, how do they interconvert, and these are all challenge. So one of the reasons these challenges for kinetics, so we know also mass action law, we may do these rate equations. We actually need to know the coverage. So coverage is basically the for surfaces, I think is a 2D. So coverage, that's the equivalent to concentration of the species. So you need to know how this concentration evolve over time to decide the kinetics. That's how what's the rate, chemical kinetics is all about, like how the concentration changes. But just to get the concentration profile information from this is actually not trivial. So this is just IR on some surface. We don't know how what bigger the area is and what is the absorption coefficients, this kind of thing. That's it's one challenge. Just get the data to be usable for kinetic modeling, and then after you have the data, then you have to do modeling itself from the data. But there's a lot of challenges, which means that there's of course a lot of work for us to do, like theoretical computation. So, and that's how I got involved in this, and so I'm trained as a quantum chemist, so I'm studied as DFT like a mechanics, something like this, DFT mechanics. Anyway, so of course we use DFT to do a lot of things to understand the atomistic details of structure and the interaction between molecules and molecules with surfaces. It's a very powerful tool. We can talk about how the many problems with DFT. However, DFT is popular also for a reason. That is, can give you a lot of information if you know what the limit is, right? So be careful with that. So, of course, then we will start with just using DFT to try to understand what the configurations on the surface and what are these IR spectrum telling us that from the experiment. So, so I'll talk about DFT. I will mention. When we use DFT, it's always be helpful if you are aware of the inaccuracies within DFT, and find a way maybe to correct it, and so that you get a really useful information from DFT calculation. So I will talk a little bit about that. So this is the kind of outline of the rest of my talk. So with the DFT calculation, we're trying to tackle the idea, the problem with how you process the experimental data to get the coverage information. Yeah. So then on the other end, so I'm talking about the machine learning methods. So here, the machine learning, what I'm doing here is again different from what Mikhail talked about. Like I'm not so it's not a machine learning method to help DFT per se. It's not trying to make DFT better. It's more like directly using the data. It's a data-driven approach. So the experimental data, how can you can model kinetics just using machine learning methods? So from the experimental data. So we all know that machine learning is actually data is very important for machine learning, and so in picking the machine learning methods, so one of the challenges for science, like an experiment, is that there's always not enough data. So the data is we have maybe different temperatures, but each temperature has a curve. That data is still not enough for black box training of any machine learning model. So you need a large amount of data to actually train a robust machine learning model. So that's actually another use of DFT nowadays. It's actually to generate data for you to train your machine learning model. So that's because the experimental data is hard to get, but the calculation data is relatively much easier. So here, because we're using experimental data directly, so there's so you have to be very careful with overfitting, of course. So we choose to use a model that actually are physically interpretable. So we try not to do any black box model. So I'm going to touch on two methods. So the polyugenet is the one that we are developing, and the CRNN, the chemical reaction neural network, is the one that we learned from other people, and I'll show you how that works. All right. So let's get on to the first part, which is the DFT part. So again, so we're trying to understand the experiment. So it's good to ask what you already know experimentally, right? So CO, I mean, carbon monoxide absorption on metal surface is like it's like a fruit fly for surface chemistry. You know, it's well studied, and so there are a lot of things you already know. So I mean, the like for the different coverage, like a lead, there is a low no electron diffraction, like there's a surface pattern. It will tell you already what the structure is on the surface at the 1/3 monolayer and or at a half monolayer. So these are all the structural information that are already available just experimentally, just by looking at the diffraction patterns on the surface. So we should be able to reproduce that. The other thing, of course, you know, is the frequency, CO frequency as a function of the coverage. So in this coverage, I mean, you established by like at the maintain different CO pressure for the in the chamber, and then you can because you have the well-known pattern for the 1/3 coverage, right? So this is where once you have this, you can pick one point here, which is exact, you know, and then the rest of the you can just by comparing the area, so you know what our coverage is at different point, and also the wave numbers, the frequency, how these change. So these are the experimental data. Is pretty old, but they haven't changed much. Right? And one thing you notice here is that in the IR, so you see this kind of curve, there's a sudden drop when you increase coverage, but then there's also a flat part on the top, which is at the low coverage. So those are the two things that are very important features on this, and we will talk about a little bit more later. So those are the experimental known things. Now, with DFT calculations, okay. Again, this is done by many people already, DFT, and so it's a well-known system, CO absorption. And so just give you, for people maybe haven't done this kind of calculations before. So the setup of this is just you have a slab model. The slab is kind of like a few layers of the palladium metal. So it's periodically repeated and then XY direction. So then on the Z direction, of course, then you have a large vacuum, like a 15 angstrom vacuum, so that you don't have this kind of big interaction between these slabs. So now this XY direction can simulate the surface, okay, and then you put CO on top of that for absorption. So you want to make this like a real metal. So you want to fix the lower part of this slab to the bulk property, bulk parameter. But then you also want to simulate the surface. So you want to relax the top 3 layers of this palladium atom, so that the structure will kind of more like the surface structure. Okay. And then when you see, you can put on different side on surface, like you have 1-on-1 surface. You have hollow side. Hollow means you're coordinate with 3 palladium atoms. We have bridge side, which you can coordinate with 2, and then the top side. On top side is just coordinate with 1. So for the coverage, we are starting here. Then in that experiment, it's pretty low coverage, so less than half half monolayer. So only the bridge side and the hollow side will be starting. So now these are the setup of the DFT calculations. Now this has done again by many people, and then now people have, I mean, for many years, people find that the DFT actually is not very good in predicting the binding energy of this CO absorption on the metal surface. Okay, it actually even got some like a very basic question wrong, like especially like for platinum surface. The most stable configuration experimentally to know is on top side, but the DFT calculation they always give you the hollow side as the most stable configuration. So these are again because it's such a big failure, so a lot of people started it and also have good understanding of why this happened. So this can be explained by this model, where the black hole model for CO binding coordination. So here you see this is adapted to to a metal surface. These are the orbitals, frontier orbitals of CO. You have the HOMO is the 5 sigma and the 2 pi star as the normal. So and this is the band structure of a metal. So for the the binding of CO to a metal surface, what happens is basically based on this simple orbital interaction, you have this of course a donation from sigma to the empty, the vacant band of the metal, and is not a near band, is the community. And not a different band. And then you have the back donation of metal d orbital to d electrons to the 2 pi star orbit. Okay. So it turned out that in DFT there's a well-known problem with the underestimate of the LUMO. The LUMO always come out too low with DFT calculations. I mean, it can be corrected if you use the exact exchange, but with surface studies, the periodic system, exact exchange is out of question actually. So it's very hard to do. So with all these local and semi-local functions, functional, you always get a very low LUMO on the field. What that means, then you have this is too close to the Fermi level on the value, so the back donation will be overestimated. So the back donation is overestimated, which means there were overbound CO, because it's kind of like an interaction between CO and the metal is now being overestimated. And this overestimation is not equivalent among different sites, because when you have 3 metal atoms, like a hollow site, so you have more back donation than when you have only have when one metal atom is connected to CO that are on top side. So that causes the more overestimation on the hollow side than on top side, or on the bridge side. So those are the again understood. So maybe we will know why DFT is not very accurate for this. So then, for practical reasons, of course, then yeah.
And you say this is known for local and semi-local functionals. I wonder about the scan functional. Scan should somehow, my mind, correct for some of these problems, but I don't know, do you know?
I haven't followed up on the new study of scan. Yeah, I know scan is much better than.
It's not right.
I read the previous paper.
Oh, okay.
Yeah. Yeah, it's the same problem.
Same problem?
Yeah.
Okay.
Same problem.
Was worth to study, I guess, but.
Yeah.
Sorry.
Yeah, you don't get the I mean, you didn't get the order right. The stable
Order is wrong.
order is okay. That's right. So apparently having more advanced functions does not help. So turn out that actually simple fix doesn't help. If you know what the problem is, you can try to correct it with some empirical approach. There's a little bit. So the correction we use, there different ways to correct it, of course, right? The correction we use is from this paper. So by the way, she's the first author on that paper, Sarah Mason. She is our new group leader at the CFN theory and computation group. So yeah. I'm in the theory and computation group, so she's my group leader. That's not the reason I use this, of course, right? Because this is really a simple correction, and I know other people also use it for CO corrections. I guess I'm aware of this paper because of her bringing up to my attention. So now the correction is like this, because this problem is due to LUMO too low. So the low LUMO in DFT also can be associated with too low excitation energy for the triplet. So because the triplet basically is flip electron from a HOMO to a LUMO in the simplest picture. So then the low triplet energy will be also be too low, and that kind of correlated with the where the level of LUMO is being correct. So here, what they found out that there's a very good linear relationship between this single triplet in CO and difference and estimate of the binding energy, the chemical energy. So now, if you want to get the correct binding energy, now you can just find the correct singly distributed gap, and use that point as your correct binding energy. So the correct singly distributed gap the base can be calculated from CI calculation. So that's a CO molecules naming in done before. So now, if you use this value, I mean the chemical absorption value at this point, then that will be your correct binding energy. So by doing this, basically you can produce produce a kind of correction curve, some correction terms for different configurations, different metals. You can do each one has different corrections now. So now, if you apply that correction, see here, I highlighted the platinum. Remember, I told you that platinum is the catastrophic failure for DFT. I mean, CO absorption because it got the binding site. So if you do a DFT, like you have this. So here, your binding energy usually like because we use the larger the better. The negative term of it. So you see the on top side minus hollow side. The DFT has the on top side actually has smaller binding energy than the hollow side. After this correcting, you get the correct one. So the correct order. And so for palladium, the system that we are studying, this DFT is not that wrong. It's actually okay, but still we want since we have this corrections available. So we want. Oh, thank you. Like this. So we want to also apply this correction to the calculations that we do. So that's the again about the binding energy. That's how we calculate get our data from. And if you apply those binding energy corrections, and these are the results for different coverages. So the way you have different coverages, right? So you have one CO molecule in maybe in a some supercell. If you increase the cell size, then you have a lower coverage, right? Because the coverage is really about how the ratio between the CO and the number of palladium atoms on the surface. So to get to a really low coverage, which means you have to go to a big cell size. So if you get because you have 6 layers of them. So you increase the cell size by double, you have to increase the whole slab by double the slab size. So the computation cost actually can increase pretty fast. That's why previous studies they haven't really gone to very low coverages. So it's very costly to do this. So we try to go as low as we coverage as we can. So we have a 4x4 cell and 1 CO molecule in there, so you get a 0.06 monolayer. And we do it up to 0.5, so it's a half monolayer. And so again, this is how binding energy is the average of the CO absorption energy. So now there are some basic facts there is already known to most people. So for hollow sites, I mean, there are two different hollow sites actually. There's FCC and there's the HCP. They depend. I mean, ABC. When you stack the ABC, there's a different way of two different sites, and they're actually identical in terms of binding energy. So we don't differentiate them. So we just use hollow to say this 3 coordinate site. So the hollow site is the most stable for up to 1/3 coverage. So which is not surprising. Experimentally, they also know that. So 1/3 coverage is 1 CO coordinated to 3 palladium atoms. So kind of saturate your hollow site, for instance. So now after 1/3 monolayer, you have both bridge and the hollow sites now being occupied. So they have the coexistence of these two. And then even the 0.5 monolayer is both still coexistence. I mean, do you have a pure bridge site configuration? But you also have some other configuration nearly degenerate, very close in energy. So these are coexistence. And another thing I want to point out here is the data. We went to really low coverage, right? But we still see this binding energy increasing. So that's due to like interaction of CO, right? And I will talk a little bit more later also. And this is also important for the IR frequency. So this interaction between CO when they're on surface is actually much longer distance than when they're in gas phase. Now because of they can now interact through the metal, the D band and the electrons on the metal. So yeah, okay. So we haven't reached the saturation there. Yeah, even we went to a very high, a very large unit cell. So now that's a binding energy. So here the frequency. Okay, so there are a lot of things going on here. The first of this process, these are the data points we just extracted from that earlier paper I showed you, experimental data, where you see there's a saturate, kind of flat here, in the low coverage. So the blue and green are the two. They are both the same data, but just applied a different scaling factor. So it's common practice, right, in even in gas-phase calculation, quantum chemistry, where you for CO, for any vibrational frequency, you apply a certain scaling factor to match the experimental value. Even though, this scaling factor can due to many reasons, mostly because of the computation method is not accurate enough. So the scaling factor, of course, you can come with different ways. So if you compare here, let's say, if we use the gas-phase CO frequency and compare that with experimental gas-phase CO frequency, I will get a scaling factor of 1.0008. That shows the DFT inaccuracy for the gas-phase calculations for the CO for the vibration. However, that you can see that does not match very well with the experimental data. Instead, you have to scale it to 1.016 to match the experimental data better. Especially in this part. I'll talk about that part later. So, and we think that there's a reason for that, right? Because again, CO on metal surface is different from CO in gas phase because of the overbanding with the metal. So overbanding with the metal, which means, so when you bind to the metal, to the back donation of electron to the 2 pi star orbitals. 2 pi star is the anti-bonding orbital. So that will when you occupy 2 pi star, you're weakening CO bond basically. So you're getting a lower CO frequency. So now if you over estimate the back donation, you basically you're over weakening that CO bond. So you're basically make the CO frequency even less rigid. Make the CO bond less rigid because of the calculation error on the surface. So that's why we think on the surface there's for CO vibration frequency, you actually need a larger scaling factor than what you have in gas phase. And this scaling factor will be different for different site. The harder side will be larger than the bridge side. So this is kind of similar to what you do when you correct the binding energy. Now you have to apply the same logic to the correction of the CO frequency. So when you do that, you get actually pretty good agreement between the blue and the red for between theory and experiment up to a point. So this range is pretty good, and then it start to deviate again. Okay. And the reason, so now we experimentally they explain this flat behavior as due to island formation. Because it's not clear why the island will form. CO, if you think of a CO absorbed on the metal surface, CO is a dipole, as a dipole, and they're all absorbed in the same direction. So this dipole direction, I mean, the same direction of the dipoles, they repulse each other. The CO, if you just put CO on the metal on the surface, they should just disperse. I mean, as far apart as possible. So that's what actually DFT calculations showed. I mean, if you just make the cell bigger, lower coverage, and the CO will just be further apart from each other, and then we have that, so the interaction between them, even though there's still long distance through the metal, but now become weaker. So you will see this kind of change on the in the frequency of the CO because of this frequency. I mean, the interaction become weaker. The distance become bigger. But experimentally, somehow they have this flat behavior. Even though it's explained by island formation, but we really don't know why it happens, and whether it happens or not, actually, it's not clear to us either. So, by the way, this is I don't know. I don't think it's seen in every experiment. So maybe there's some experiments don't see the island formation, but they don't have good data showing you what the frequency is. So this is the part we don't have not been able to reproduce, but we think in this case the calculation is good. Is actually has a good foundation of why it happens. So now, okay.
So, because the calculation, you are calculating the vibration frequency of single CO.
Single CO, yes.
Yeah, but when the COs are actually, there are many COs. In fact, there can be also delocalized vibrations. You can think of the linear combinations of each CO mode.
Yeah,
So
true.
especially for high coverage limit, how do you know whether the experiment is measuring the kind of the average vibration frequency instead of the singles? Because of the dipole interaction,
Yeah.
I think anyway they will form a band of vibration forms.
Okay, that's a good question. So
Yeah.
when I say actually when I say single CO, it's single CO in the unit cell, right?
Yeah.
So when I actually when I do find a difference, just manually remove the CO coordinates.
Okay.
It's done in every unit cell.
Sure.
So which means this vibrational is actually due to it's already a coupling of all the COs on the surface, but it's only one way of coupling them. This is in phase coupling, right? They're all just moving in sync.
I see. So your calculation actually is the normal model analysis of the aggregate of CO vibrations.
It's aggregated, yes.
Yeah.
It's so that's why you have this interaction information in there, by the frequency actually changes due to when I change the size. Yeah. So yeah.
But following up, but you could do a supercell calculation and have the full picture, no?
I can, yeah, actually we did. So basically you're saying like for the same coverage, like I can do a double the size. I can use two CO molecules or even bigger. Just for example, argument, right? Just double the size of two CO molecules. I can then just move one CO, not the other one. So I can have this the coupling like maybe now it's half of the strength of the coupling now of all the COs now. So yeah, you can already that you can see some change in the frequency. Yeah. So yeah, I mean, of course, the question is which one we use to compare with the experiment. So we use the one that, I mean, in some of this thing we actually have more than one CO molecule, right? When I do irregular, I mean, similar size, I mean, the coverage to enable to, in order to reach all those coverage numbers, you have to change size and number of CO molecules. So some of them have different CO number of CO molecules in there, and by the way, to be consistent through all the calculations, we always choose the vibrational frequency where all the CO are moving the same way, because that's how it is when you have a single CO in a small cell, right? That's So even when I have more than one CO, I still choose that mode. They all move in the same in same place, like to report. And that's actually the largest frequency. So when you couple them, this one, the all moving phase, that give you the biggest frequency. If the auto phase, they have a smaller frequency.
So in terms of the final difference method, you actually stretch one CO.
Yeah,
And then see the time dependent displacements of that CO.
I just calculate the force constant.
Force constant.
Yeah, Hessing. Yeah, use Hessing too.
You calculate the Hessian matrix.
Yeah. They call it dynamic matrix
Okay.
in WASP,
I
but
see.
it's the same thing. Yeah. But I only move CO because assuming it's decoupled from the movement of the metal atoms. So all the palladium are fixed. So only the CO.
How about the distance between the carbon and also metal atom? Do you make it? Is it
Distance
fixed?
between the carbon atom and
Yeah, the metal atom.
these are okay. So these are we start from optimized geometry, the relaxed geometry. So then you just move either C or O around the equilibrium position.
Okay.
Find the difference maybe
Yeah.
positive, negative by certain amount, 0.05 angstrom, small perturbation. Yeah.
I see.
Yeah.
And then you displace and then you calculate the
Energy.
energy.
Yeah, you calculate energy gain. So you have you basically trying to find the difference to get the Hessian matrix. You have
Okay.
to displace it by twice, I guess. Yeah, get the 5 points, and they can. I mean, there are different ways to approximate the Hessian matrix. I think the one we use is the central difference. So they have moved in either direction by two of the steps. 0.015. So yeah, it's approximate, of course. It's not. That's why we apply all the corrections. The hope is like again error cancellation. The error is consistent among all the calculations, so that its trend is good. Yeah.
So for each CO, how many motion degrees of freedom do you have? Only one for each CO?
Well, we let them actually all the 3 coordinates change,
Okay.
but it doesn't matter as much because in the end it's the one that along the Z direction that gives you the frequency that you want.
So the dimension of your Hessian matrix is 3n if there are n.
Yeah, 3n, yeah.
Carbon monoxides.
Yeah.
Okay.
Anyway,
So is that your understanding of the difference between the flat experimental line and the slope of the calculated line and slope coverage? Is it fully the difference between the collective, the in phase and random phase? Is the calculation or is it more complicated?
that's a good question. You're saying that maybe experimentally you see a different mode, not the one that I calculated.
I mean, the in phase, you're changing, I guess, effective electron density in the metal and then affecting the mode slightly, right?
Yeah.
The random phase, and that's a very local effect.
I see.
Is that your understanding of the difference?
Okay.
What phase are you talking about?
He's got all his vibrations are in phase, and
Oh,
so the frequency he's calculating is the reaction to that in phase vibration, where you're modulating the interfacial charge density.
That's a good question.
Would be if they were random.
Yeah.
All of them will come out as different normal modes, right? Yeah, different phonon normal mode. Yeah.
Well, you change the stiffness of that bond because they're on the phase, you change you're modulating the interfacial.
So because
charge density.
I guess what I'm calculating is the coupled or I mean CO move in the same way because that's the limitation of the method, right? You can move one, they all move in every unit cell.
Okay.
What I think Matt was saying, like, I mean, what if they're not there's no correlation between these movements, right? Each one is like a localized IR. If it's localized, just due to a single atom, then this coverage effect should be not there. So it probably should saturate
Yeah, there's no long range interaction.
Yeah, no, no.
Yeah, that's why actually I asked about the spot size of the IR. I think it must be pretty big, and then within the IR should mostly likely to detect
Okay.
or delocalized vibration, right? Because unless the coverage is very, very low, there can be many CO molecules within. Of course, it also depends on the localization methods. So I think it's an interesting question. So,
Yeah,
how localized the vibrations are.
yeah, yeah, that's good, yeah, I mean, for because computationally, we cannot really just localize one CO molecule on the surface. But I have to, yeah, go back maybe to read the experimental paper, better see if they actually detect the local, because the local mode, like a CO vibration instead of this delocalized.
So, would it be kind of, so are you only solving at the Brolin zone, or are you gonna solve this? Because I mean, even if you only do finite displacement of a single CO mode in your unit cell, if you solve that at different K points, you will actually get out of phase vibrations across unit cells. So it's only at the Brolin zone that you'd actually see the in phase motion. Right, so it's the same thing, right? I can solve any periodic system either by making a supercell larger and having more finite difference calculations.
Okay.
Or I could have a single unit cell and solve as a function of K points.
Yeah, okay.
Right, and I get this, in principle, I can get all normal modes out of those two calculations analogously. It's just how much am I solving in real space versus K space. So I guess I'm curious, are you only solving at the Brolin zone, or are you actually doing K point sampling for the vibration itself?
Okay, so are you, I guess you're talking about the sampling of the phonon.
Yeah, the photo, yeah, yes, correct. The
Yeah,
K
so
points of
we
the photon.
we are not sampling, yeah, doing any phonon sampling actually.
Okay, so
yeah,
you're literally just getting the in-play.
Yeah,
acoustic light at the Brolin zone.
yeah, we only sample the electronic structure, yeah. This is, yeah.
What about non-adiabatic effects? Do they matter here? Like
No,
the fact that maybe the vibrational frequency of CO can be affected by the fact that it's not vibrating in the ground, born Oppenheimer surface, but in a more complex set of surfaces, given there's a metal, with many surfaces. very
You
close
mean
to
like
each
the
other.
company between CO potential and surface with
And electrical
metal?
pairs in the metal, yes.
Hmm. I mean, all calculation is adiabatic, of course, that's for
So
sure.
you have
Yeah,
one surface.
yeah, but
But in reality,
reality is still, I mean, the excited state is so high. I don't know if it really matters that much.
but even for the metal.
For the metal, of course, you have continuum, yes, there's a lot of states there, but that might be, I don't know.
For scattering of hydrogen at metal surfaces.
Yeah,
That matters a lot.
I know,
So that's an interesting question, though. So, but that's a scattering experiment,
yeah.
right?
Here, vibration also, right?
Right, but I guess I'm curious, like, because you do see this, I mean, you know, it's a different than all these people look at all these Many-Electron effects, but usually as a scattering experiment, where you come in even with a vibration that excites electron hole pairs and that either shifts your
So not for
vibration.
the fundamental vibration.
I don't, if it's
Yeah.
truly an absorbed thing, I don't think that's the case. And it's just that you will end up with mixing of your electronic structure in both cases such that you can see a shift of the seal vibration in comparison to the gas phase due to the mixing. But that's not really a non-adiabatic effect, it's kind of more of a broad electronic structure. So that should be captured in a ground scale.
Yeah.
To my
Yeah, I agree, yeah. Okay. So yeah, that's good, very good point, for this company, CO model, whether we are calculating actually what the experiment showed us, that's always a very big question, you have to talk to experimentalists to make sure you are actually calculating what they do. So I have to go back and think about that more. But the main thing here is like, I guess, just from the calculation alone, it looks like there is a good correlation between just coverage and the frequency. So just from frequency, you can just tell what the coverage is, right? So even when there is a mixed like sites, like a hollow and bridge, they kind of like a change continuously. I mean, there's a different slope because once you have bridge site, it's a very distinct different frequency, so that will change the slope of this. But overall, it seems to be like well, if you can find the frequency at all the coverages, then you should be able to take what the exact coverage is. But the problem is again when you have the real experimental data, then it's not as easy. So we calculate just what it's like ideal system, and we get a single peak, a single line actually of what the frequency is. Experimentally, it's very hard to get what the peak is, especially if you don't have enough signals. So like these are experimental data. So in most part, when they have high coverage, they can more or less identify where the peak position is. But when this coverage gets low, it becomes very noisy. It's very hard to tell where the peak position is. And sometimes you just give up. Like, so all these data points, like you don't know where the peak is, just give up. They don't assign peak. So now this is not helpful. Even if you have a perfect correlation between coverage and the frequency, and you cannot get the frequency from experimentally, so you still don't know what coverage is. So then
what the different numbers?
what different? Oh, the temperature. I'm sorry. Yeah,
Temperature.
yeah, different temperature. Yes, that's very good. Okay, so now of course in the spectrum you can even if sometimes if you don't have a good peak, you still can get the area of the absorption. You can accumulate all the part under your line. So the area data actually, if you just take the area, of course you get more data points. You can go even at a very low coverage, you still have some absorption there, and you can show kind of well behaved and the average and the area decay as you dissolve. So these are giving more data, and this we would like to use this data to get for us to be able to model it. The more data, the better. The question is like, how do you get the coverage from the absorption area? So because this is not a, I mean, it's not the standard thing. You have to, I mean, always use it's kind of arbitrary units there because the surface size and also each experiment will run. You may have a different surface condition, a little bit different, and all those things. And also the absorption coefficients can be different when you have different species and different coverage.
How do they get area experiment?
Area is just by integration of you draw a baseline and you just integrate the spectrum about that baseline. Yeah.
Oh, you mean the spectral area?
Spectral area, yes, yeah. That's from spectral, yes.
Okay, yeah.
Spectral area, yeah. So, yeah. Anyway, so this is again the challenge. Like the absorption coefficients is one of the big challenges because we don't know what it is. You can change with temperature and also with coverage. So now, okay, what we have been doing is kind of like using both the frequency data and the spectral area data. So because for the frequency, for a certain coverage, we know there's a distinct frequency, right? So you can pick in your spectrum. It's for a specific frequency, you can say with some certainty what the area is for that frequency. So and you can then use the area, a spectral area at that same spectrum, and then take the ratio between this spectral area and the actual coverage derived from frequency to give you the absorption coefficients. So that's doable for some of the frequencies that you know it's well it's actually represent the experiment and also the coverage. So So you have pick up some of those points where you are very certain about, and you get the absorption coefficient. So now you can use that absorption coefficient for the low coverage part. Then you just we just kind of assume it's now not changing anymore. So because it's all hollow side and small changes. So we just use one of the absorption coefficient to enter the area for the low coverage, the decay part, to get the coverage. So for the high coverage, then we kind of do just a simple linear interpolation of the absorption coefficient. So that's how we kind of like using the both frequency information and the spectral area information to derive the data, which is the coverage data. The coverage data will be the concentration profile for each, I mean, at a function of time at a different temperature, and that will be the one that they actually use for modeling, for kinetic modeling. These are the information of kinetic thing. So that's kind of the first part of it, right? This is just the how I get the data to be usable for kinetic modeling. So this is, and then here we show that you can actually, I mean, you can do DFT calculation to help you understand the data better. But I mean, there's still challenges when you deal with real experimental data. So you have to find ways to take the what's available to you, and you have to make some further approximations to in order to get the coverage data. So knowing the, I mean, the DFT part of was knowing what's not working with DFT, like the inaccuracies of DFT, will help you also to get a better insight from DFT calculation. Now I'm going to switch gear to the second part of this project. Now, assume we have very good kinetics data now, transient kinetics data. So this the quality of that transient kinetics data is still debatable. You know, we a lot of approximation is used there. But now let's assume we have very good data that they form maybe some of math experiments that have really high quality data. And what can we do with that data, transient kinetic data? Right? Can you just derive kinetic models from this data alone? So transient kinetics data, right? This basically is a concentration change as a function of time. That's a very simple, very it's a time profile for different species. Okay, so you may not get every species in your data, but you have some data like representing the concentration of the different species there. So can you get a kinetic model to meaningfully represent your data? So, and so this is the data problem, right? So you have data, and then of course you want to be able to derive the model directly from the data, and then machine learning will become a very useful tool for that, because what machine learning methods do is just find the correlation, find the what's hidden in the data. So the problem with machine learning, right, with especially the deep neural net right now, is there's so many parameters, and the structure of the machine learning models is really not transparent to users anymore. Right? So you don't know how to interpret this machine learning model. You may get very reliable predictions from it, but you may not get it. But you don't know what your limit is sometimes. So with the limited amount of data we have, we want to be able to interpret this data. So we want to have some model that actually is a physical model instead of a black box model. So that's the main goal of when we use the machine learning approach. So I'm going to share with you a couple of methods. One is our own, and the other is we learned from other people. So to set up the stage a little bit, what you are trying to do here, what we're trying to do, so it's kinetic modeling there's a kinetic model. Basically, is like this. You have a kinetic model. Three parts of it. You have kinetic model. From this kinetic model, you have the rate equations, and this rate equations you can derive the basically a set of ordinary differential equations that tell you how the concentration change, and from that you can get the profile the time variation of the concentrations. So that's the three part of it. This is the inside of the chemistry. What the mechanism is, and this is usually what you have in experiments, and this is the kind of underlying mathematics, well, how I connect this to. So now, so in direct modeling, you already start with the model and then some reaction network, and then you have a estimate of this rate constant, and then you can write down the differential equation, ordinary differential equation, and then you just do integration of this, then you get the profile. So that's a direct model. So what we mean by inverse modeling, because in experiments you get this first, you got the data, and then now you're trying to reach this, right? So you can find what the mechanism is. So what we are asking is like, can you directly derive this set of equations from this data? So because this data supposedly has this information in there, the differential, the dynamics. So, and from here now maybe you can just try to derive the mechanism. So that was the approach we were taking. And it all, of course, it helped a lot by the development within the machine learning community. So no, okay, I'm not by any extension measurement expert in machine learning. I don't know much about what is machine learning method, neural net, convolutional neural net. I never used them. But here it caught my interest because there's a connection between the machine learning models and your dynamics in your system. Okay, the connection comes from because with a more and more complex deep neural net, the deep neural net. So you have a input layer and output layer, and then you have some hidden layers in between. They're all connected. And each layer has many neurons, and you can connect those neurons by different weights, and each weight is kind of parameter, right? So you can train them, and you can add more and more layers to that model. So that the more layers you add, the deeper, and it's called a deeper neural net, right? So and you have more parameters, and you get of course you can get a better fit. But at some point they found out actually when you just simply increase the number of layers of the deep neural net, it does not help anymore. It's actually getting worse. The performance of the deep neural net. So each layer you only talk to the layer above it. So you direct output, take the direct output from the last layer, and then they use it as the input. Then get some output on the next layer. So that was the original structure of the deep neural net. So then when this layer getting too deep, to have this problem of vanishing gradient, so that you cannot don't know why it happened, but it's basically you are not be able to optimize the model anymore because this is because the relationship become too complicated. So what they have done with what they call the residue network, they fix this problem by now in the layer when instead of simply taking the output of the last layer, it also adds something from previous layers. There's some function you can optimize. So to keep some information from previous layers available for this layer to be added, so that you can actually overcome this vanishing gradient problem. So by doing that, it turned out that this kind of layer structure it now becomes very similar to a kind of a differential equation. Discretized the differential equation. So when you have time evolution, basically the time step, next time step is this time step add some terms, right? This is how you discretize it. So this kind of relative network now becomes a kind of like a ODE network. Okay, that's what they do. And they have and this is one of the original papers to derive this and implement it. So, okay. So now this is exciting for us because if you flip it around, so now deep neural net you have now becomes an ODE network. If you, on the other hand, which means if you have a set of ODEs, you can train it like a deep neural network, right? So if you just give even some physical ODE systems, so now you can use this all the machinery, all this automated differentiation, or background creation, and maybe hyperparameter tuning, and you can use those to tune your ODE model, right? So that's what we find is really exciting. That between this connection between this physical problem and the machine learning. So we so what we're doing, I'm going to show you. So it's basically trying to use interpretable physical models as the underlying ODE system, and then use it for the machine learning training. Okay. All right. So then, what is the? I mean, when you only have data, when you don't have any much information about the system, so what is the model you have for the ODE? I mean, based on the rate equation, right? You have. I mean, I showed you earlier that from model to ODE to data. So the ODE basically is a set of polynomial terms, right? So in the end, I mean, no matter what your reaction is in there, it all comes down to those polynomial terms. Assuming, of course, mass action law is the one that's working there. I mean, if there is a heterogeneity in in your system, then that's you have to account for the transport problem. That's a different set of equations. But assuming you have a homogeneous system, then you only have the mass action law in play, and all the ODEs will be just polynomial terms. It depends on the interaction between just different species. So, I mean, if you don't know the mechanism, so of course you don't know which polynomial terms should be there. So, again, for the most general case, then you just put all the polynomial terms in your model. Right? That's what this represents for a 3-species model and system, and all the terms, like first order and second order terms, I kind of excluded some of the self-interaction terms. You know, there's no square tape here, but the other terms are in there, and for all these terms can, in theory, show up in the equation for each of the rate. I mean, the production rate of any of the species. So. So this is the most general model for the ODE in a kinetic system, but of course this is too general, because the parameters, these are all the parameters, right? Increase cubically with the number of species. Okay. So we have this problem that this is too many parameters. Cubically, because like this, I mean, the second order term is already square, and we have this for every species. So that's cubical scale. And so
is it quadratic? Is it cubic or
Q?
Yeah, the vector size will go like quadratic. It will go quadratically. Right?
This will go quadratically, right?
Yeah. Then the matrix will.
The matrix is goes linearly with the size of the. I mean, this dimension goes linearly.
Oh, okay. That's okay.
So I mean, this is we already use some chemical information here. We just limit it to second order term. What that means is like for chemical reaction, the kinetics second order, which means just two species come together to react to produce something new. And the reaction rate is just what's likelihood of those two coming together to produce something new. And I mean, chemical reaction, of course, very unlikely. It's very rarely seen three species coming together to produce anything new. So the reaction, third order reaction is very rare. So that's why we are using this. So now this is the very general model, of course. I mean, you can still already make it work, like by just I mean, initialize this. I mean, this you have to make a guess what's number of species in the system. That's the kind of input parameter. And there's a concentration data is like your training data. And for integrate ODE, you really just need an initial condition. Right? Once you have the model, you only need to know what the initial concentration is. So you can do this and you can and you design some kind of loss function. This is kind of standard like optimization loop. So, and once you converge or just run enough iterations, loss function is low enough, you have some set of polynomial rate equations for each species. And that's actually not just the rate equation, but you also have this predicted the concentration of each species, because that's just from the byproduct. And loss function, you can design one like where these two. I mean, you can since you have some target data, you can just try to match the target data. Take the means square error of this. You can also apply some constraint. So of course, the concentration data cannot be negative. You see, you can put it with or the negative one has to. I mean, no negative one. And you also can have some other condition you can use where the you say this. Sometimes you don't know the concentration of individual species, but you know the concentration of the sum of different species. Yeah, it means IR maybe you're only tracking maybe certain frequency, but that frequency may show up in different molecules. So you in the end you have this just two species together, right? So those are the so you can apply those kind of different constraints. And mass conservation actually is another big constraint you can use. Now. So okay, so show you the case study work. It's a simple case, just to show how it works. This is the comparison of two different mechanisms of the same reaction. I mean, the net reaction is the same, so it's basically A plus B equals to C. But this is no direct route for this. Are you coming? Yeah. Wait. Okay. Okay. So you have to go through some catalyst. So this intermediate, I mean, mechanism can do either one step, I mean, one intermediate or two intermediate. So either A plus B only or B plus both A and B goes to D. So one or two intermediate that were two different pathways, and these are the profiles. So we use synthetic data. That's I mean, just for test. The data is produced by integration of the ODE that we already know. So you now use the data you're trying to derive now the model, your model back. I skip some of the details because again, you get so many parameters in there, so I have to apply some knowledge to that can eliminate a lot of parameters. Yeah, the parameters is too many, and the data is not enough to get all the parameters out. So we have some constraint for the mass conservation. And if you do that, and you can get for these two cases, actually, you can get this is the two intermediate pathway, and this is the one intermediate pathway. How do we know it's one intermediate? Because one of the concentrations intermediate F. So we use the same model to train these two for these two cases. But as training result, one of the intermediates is always zero, has no contribution. So that's what I mean. This is one intermediate. And these are the results of this rate equations. So this rate equation, of course, then you can compare with your ground truth. And so when you compare the ground truth, you see this. Of course, not very accurate. I mean, there's the model, like, the sensitivity is not high enough for this. But the more problem is like this is with even the immediate many terms, there's still other term there in the equation that it is not there in the actual mechanism. So we cannot get the exact terms out. We get the dominant terms correct. And for this method also, there's a problem because we do this for each temperature. You can then you can make maybe you can do it. I mean, based on the results to get temperature effect. But it would be nice to have a method where you can use all the data from different temperature to train the same model. But that give you more data for the same training. So that's how we are really excited for this work. This is from a group from at MIT. So it's very interesting work. It may take more than 5 minutes to explain, but I guess you can just go to read the paper. And the idea is like instead of just going after the polynomial, like what we did, the polynomial rate equations. I mean, there's ODEs. They're actually going after the actual reactions. So for each reaction, you can write the rate equation like this way. So it's based on the stoichiometrical coefficients, and this can be really arranged into this form. So, and here you have a bunch of inputs. I mean, this can be used as input, and this exponential function can be mapped in can be used. Actually, you can just use some activation energy in the neural net. Okay. So what this means is this structure of this rate actually maps very well with the neuron in a neural net. So what this neuron is like, you take an input is the log of these concentrations, and you apply the weight. The weight is basically coefficients, stoichiometrical coefficients, and you add them up. You get and then you can also add the temperature effect here directly because there's a Arrhenius law, right? And add them up, and then you apply some activation energy. In this case, the activation energy is just exponential, and you get the rate, the output. Now the output is just multiplied by the stoichiometrical coefficient again. You get the rate for the change of production rate of species. This is one reaction, and if you have more than one reactions, you just have a given a neuron. And this neuron, these weights are just represent the stoichiometrical coefficients for different reactions. So, and so this is really a nice way of mapping the elementary reaction to a neural net, and it's still interpretable because all the weights, you know what I mean, and there's no like a magic parameter. The parameters also have physical meaning. So, and activation energy is the one parameter that you can get to. This is really nice. So we, of course, we have found. I mean, it's a better method than if it's a better method than ours. Of course, we're going to use it. And our purpose is to get to actually understand the experimental data. This is just showing what the what would be a typical output of this. I mean, this is stoichiometrical coefficients as the output, and you can derive the reactions from here. This highlights actually this is a neural network after pruning. Pruning means you have to, some of them are when it's close to zero, you have to kind of set to zero. But this highlights one problem of this method is you may not get the integer numbers of coefficients. So because this is optimization, I mean, if it's continuous, so you don't know. So if it's close to an integer, of course, you can still you can just make it like a round it off to the integer, and then you know what it is. But if it's a 1.5, then it's very hard to. I mean, it becomes hard to interpret. So that's a downside of that the method. Okay. We use this is the earlier two cases, the one intermediate and two intermediate that were we used the polyOVNet as a test case. So if you do the same thing, you can get pretty reasonable result. And here you get the direction. I mean the reaction directly instead of just the polynomial coefficients. And you can do a test, convergence test, which means like how many reactions do you need? maybe how many neurons in that layer. So here the three reactions converged, and then the loss function does not change anymore. Here you have two reactions. So basically here you have three, two intermediate, and here you have one intermediate. So that can be the good results based on this test case. And this is the last slide. This data I just got yesterday, last night from the student. So it's public quality very debatable at this point. I just give you the idea. This we're doing. This can be done now with this direct machine learning method. Yeah. So you have this bunch of data, but what this data really tells you is just the sum of these two configurations. You have a hollow side and you have bridge side. You don't know individual one. You just know what the total coverage is. So that's the only information you have, right? But you do have it for different temperature. So then how do you get a derive a model based on that? So yeah, you can build. You can assume there's a different three reactions in there or two or three reactions in there, and you apply some constraint in there. This is just the conservation of the surface side, the surface atoms that you have to be. Just the one of the complexity with the surface reaction, they are competing for the surface side. So you have to limit what the surface side available. And if you do that, then start to train, make this the loss function, and you do get some curves out. We don't know what we're still trying to understand what the curves means. But you see this here, you see there's some kind of very hard to see. Maybe you see some kind of like a competing process. This here is the bridge configuration, and this is the hollow configuration. You see kind of like this goes up and comes down. So which means there's the interconversion from one to the other side. So initially this goes more, and then some of them shift to a different configuration. So this kind of connected information now can be derived from the data. So we're still working on this, and we're hopefully agree with what was already known. Because you get some kinetic information, but some it could be totally wrong. Kinetics. So I should wrap up. So this summary of this second part, which we use machine learning methods. Well, I skip it. Conclusion, I think I skip it too. I'll just kind of skip. So this is done really collaborative work with this anybody is a very talented experimentalist. So and he's the setup, like an experiment setup, and experiment was mostly run by his student, and also done by another student, Maria. So here we is collaborating with me us on this machine learning project, and here is my group. Well, people in my group. Jay is the student that currently working with me from Stony Brook University. Tanya was a postdoc. She just finished her term. So Xiaohui is Xiaohui is actually our machine learning expert in the group. So he knows more about machine learning much more than I do. So she's funding supported by the LDRD. And thank you.
Okay, time for one or two quick questions.
Very quickly, so I'm curious, is the kinetic modeling a math, because you're doing effectively an inversion problem?
Yeah.
Is it actually a well-defined inversion problem in the sense, are you guaranteed that there's only one kinetic model that will reproduce the data?
Good question. Yeah, no guarantee. Yeah, actually, you can get more than one model. But we usually do we take it like a swamp approach. We just run the 4D simulation at the same time, different initial guess. Some of them will give you a promising result, some of them don't. If you the model make so I mean you have to apply your physics sense knowledge of whether this model makes sense or not, right? So that you pick the results sometimes in the end. You pick the model that best describe the system. But there's no guarantee. Even within the same model, if you have the same model, the parameters itself can be there's a range of parameters. We did this sensitivity analysis. it can be different by 10% or 20%, does not change the loss function much. It's really not very, I mean, I think part of the problem is there's not enough data, right? The data itself quality, first of all, that is one question, but also it's just not enough data to.
Well, I guess I'm curious, even in the infinite data limits.
Okay.
So there isn't like numerical issue. I'm just curious if this is a like mathematically, because it's, many inversion problems always end up being like mathematically.
I think the answer is still no. Yes, there could be more than one model to reproduce the data. Actually, we can show some of the mathematically you can show that with different ways of constructing a model, you get the same ODEs because from the direct network to the ODE. That step is already, it's not a one-to-one match. So same ODE can be constructed with different direction mechanism. So yeah, so this is really not end product of this process. It's meant to be iterative in some sense. Like you have this data, and then we derive possible models to describe this data. And based on these possibilities, we can suggest what new experiments maybe you can do to like eliminate some of the possibilities. Okay. So you have to supply with new additional data to be able to really pinpoint results.
Yeah, I'm sure that the inversion is ill-defined in this case.
Yeah.
How about directly calculating all the kinetic parameters and then doing the more standard way? I think the production reaction is relatively simple, so it should be possible.
Yeah. For this simple case, yeah, so we don't need to do this. Actually, this is just to demonstrate the the method work.
Yeah.
For CO, I mean, this option is already known what the barrier is.
Okay. Yeah.
For adsorption usually is barrierless. It's very fast. So, and the interconversion, I'm not sure if there is but that can be calculated with DFT, like a diffusion problem. So for this simple problem, no, we don't need this process. It's really more like a demonstration of the method, and I'll really want to study next is some actual reaction like CO oxidation on surface, or I mean CO oxidation seems to be simple either, but it's already pretty complex. Because on the surface, those atoms can combine various ways to make it species that don't exist usually, but on surface they can come together at least as stable species. So, and the more complex will be NO oxidation. So those are the experiments Anibal is doing.
Yeah.
So, I guess just with this simple example, it shows that it already takes a lot of work actually to derive this. So we of course we will still work on this more complex system, but it just feel be more careful when we do deal with it.
This is actually a big thing in systems biology. So there are, if I have to model network of chemical reactions involving 100 or maybe 1,000 species.
Yeah. For the like a big reactor.
Yeah, but I heard from some experts that even though systems biology has had long history, there were so many good papers that were not reproduced. So I think that in the chemical reaction network, it seems simple, but actually I heard from my mathematics colleague that actually there are even solving mathematically, sometimes it can be quite difficult. Okay, so I think thank you for Chen for wonderful part. Thank you, and thank you all for being good participants. So we have lunch outside here, sandwich, and so we will resume at 2:30. 2:30. We'll start with yes.